So our speaker for today is Martina Monti, and she will talk about elliptic curves over C. Please, Martina.
Thanks, Pedro, for your introduction. Okay, I don't want to talk so much today, and I want to present some of the main results about elliptic curve over the field of the complex number. So basically, I mean, I think that everyone knows all these results, but basically, one divided this talk in three main parts. So in the first part, I want to talk about complex tori and elliptic curve. In the second part, I want to talk about, I don't know, I can say morphism of elliptic curve. And in the last part, about the Jacobian of a curve. Okay, so let's start with the first part. Basically, in the first part, I want to prove that elliptic curve are topologically are the complex tori, or if you prefer, complex tori are elliptic curve. Basically, I want to show that there exists this biomorphism, and I want to recall you how we can construct this biomorphism between a complex tori and elliptic curve. Is basically what Francesco said in our first meeting. So there are different definitions of elliptic curve, and I want to take this one. So an elliptic curve, sorry for my bad writing. Okay, E over the complex number is an algebraic irreducible curve in P2 of genus 1. So basically an elliptic curve is the locus of 0 of an homogeneous polynomial. So F is an homogeneous polynomial in this variable. At priori, it has degree D, but by the adjunction, since we assume that the curve has genus 1, we can prove that actually the degree is 3. So elliptic curve are cubic curves in P2. And I just want to recall the adjunction formula. We can be rewritten in this way. If you compute the degree of the canonical bundle of that curve, it is equal to 2 minus 2 times the genus, which in our case is equal to 0, the genus of E. And by the intersection theory, this is actually E plus the canonical bundle of P2 times E. If you denote the generator of the Picard group of the projective plane as by H, we can describe its canonical bundle in this way, and every submanifold, so for example E, in this way, where D is the degree of the curve. And I want to recall that E times H times H is equal to 1. And so here we obtain this relation. And so we obtain that the D is equal to 3. So elliptic curve, you can also assume by definition, are cubic curves in P2. So this is a way to describe the elliptic curve using this cubic using a cubic equation. But as Francesco told us in the first seminar, there is also another way to describe an elliptic curve, which is the Weierstrass equation, which basically I want just to recall this equation, which emphasize the fact that the elliptic curve can be also described, or genus 1 curve, as a double cover of the projective line branching along 4 points. So the observation is that we can start from this equation, and also the vice versa, okay? Where f is described above is a cubic equation. And then there exists a change of variable plus the homogenization, such that from f we lead to this equation. To be honest, I mean, to lead to this equation, also I use the hypothesis that I work here. So in a field of characteristic 0, which in particular is different from 2 and 3, since if you don't assume this, I mean, if I remember well, if you are in another field, you obtain an equation that, I mean, it's a double cover of P1, but it's not reduced. It's not of that form. This is the point. But we are over C, so never mind. And in particular, f is a polynomial of degree 3. And we can assume, since we are in characteristic 0, that it has that form. Moreover, I assume that the discriminant of f is different from 0. So this basically tells us that this polynomial, the root of this polynomial are different, and this implies that the curves that this equation describes is smooth. Okay, so this equation is actually called Weierstrass equation, and actually it is a double cover of P1 with this coordinate branch. Yeah, branch along f, so this 3 point plus the infinite point, since I do this operation, the homogenization, infinity point. So this observation is just to recall that to describe an elliptic curve, you can consider this cubic equation. But sometimes, I mean, in my study, in my research, in general, I work with this equation. I don't know if it's more easy. I don't know. I don't know why it's better, but sometimes people prefer to work with the equation of the double cover rather than the equation of the cubic. But you can pass from one equation to another one. I mean, at least under this hypothesis. Okay. Since I want to work with an equation of that form. So this is what these are the elliptic curve. And now what I want to do is to remark you how we can relate this type of object where I, by definition, emphasize the fact that they are projective. And I want to show you that they are biolomorphic to complex tori, which basically are a topological construction. Is a quotient, is a manifold, so a priori complex tori are not projective. This is the point that I want to emphasize in this moment. So a one-dimensional complex torus is this quotient manifold where lambda is a rank to lattice, which acts on C by translation. So a priori it is a quotient, a topological quotient, but then it has also the structure of a manifold. Okay, and just to set the notation, I will denote by pi this universal cover. Okay, so how we can relate this to a priori different type of mathematical object by using the so-called p-Weierstrass function. So I just recall you what is the p-Weierstrass function. So first of all, I recall you what is an elliptic function. So an elliptic function, to be honest, you can define an elliptic function on a complex manifold of any dimension, is a meromorphic function which is lambda periodic for some lattice lambda. So by this definition, you can easily observe that if you take any meromorphic function over a complex torus, since complex torus is a quotient, these meromorphic functions must be lambda periodic. So meromorphic function of complex tori are elliptic function. And an example is exactly this p-Weierstrass function, which is a function from C to C, meromorphic, defined as following. So for every z in C, p of z is exactly 1 over z to the power square plus the sum of w in lambda, different from 0. Then I define what is lambda of this difference, where lambda is a lattice. But, well, in this case, is a 2-rank lattice. So something like that. These are complex numbers. Okay. And as you can observe, this is for sure it's a meromorphic function, and it is holomorphic outside this lambda. And since it has some poles of order 2, its degree is actually 2. So I just want you to recall some basic factor on that function. So first of all, it's not just meromorphic, but actually it is. Okay, so one can prove, I mean, you can assume this fact for sure. It's elliptic. It has degree 2. It is even. Okay, and I want to observe that from that fact we can also deduce that the derivative is odd. Okay, and more important, it was the following relation. The derivative of p at the power 2 is equal to 4 times p at the power 3 minus g2 times p minus g3, where g2 and g3 are complex number defined in a certain way. And I mean, I don't want to, okay, maybe I can recall you the definition, but it's not so important. In general, then I give you the reference of all my notes. Sorry, maybe I have to say it before, but if you define this capital G in this way, for every lambda in lambda different from 0, where lambda is exactly this one in this case, okay? Then you can define G2 in this way and G3 in this way. But I mean, our complex number in this moment defined in a certain way such that all the following relation. Okay. So as a reference, I give you the reference for all the notes of this talk, Silverman, the arithmetic geometry of elliptic curve, and also Silverman Tate, rational point on elliptic curve, if I remember the name of the book, Silverman Tatum. Okay, so why I want to focus in particular, I want to focus in particular on this four factor, the last factor, since I mean this is actually an equation similar to the one that I wrote above. Just it is we can view this equation in a certain way as a double cover, okay, branching along a cubic. So the fact is that using this is the, I don't know, the idea just to connect with a complex tori and elliptic curve using this function to interpret the p as an x of a certain projective line and the p prime as the y. So more precisely, what I want to state is that if we consider a complex torus T and pi is the universal covering, then the theorem that I state below is the following. The map phi from T to P2, which send every point that can be represented in this way to, this is the p-Weierstrass function, okay? This is the derivative of the p-Weierstrass function, 1, if it does not belong to lambda, where lambda is this one in this case. So maybe with the notation above. Okay, otherwise we send to that point if that belongs to lambda. And this map is holomorphic. The image of this map, it is this cubic equation, so it is this elliptic curve in P2. So are the point in P2 such that satisfy this cubic equation. So by definition, this is an elliptic curve. So I will denote this set by E, and it is injective. Okay, so I don't want to really to prove that that theorem, since I mean to prove the holomorphicity, you can use the local action to the local, sorry, the neighbor. I mean, you can work locally, okay. And for the injectivity, actually, you can do by absurd using, but you have also to use the expression of P, which I recall that it is this one. And to show point B, you must you have to prove both the equality, but the inclusion, but it's not so difficult. The point is that if you assume that the theorem, the corollary is that every complex torus is an elliptic curve. So in particular, every complex torus of dimension 1, maybe I have to, but in this case I want to talk to you about only so one-dimensional complex torus is an elliptic curve, so in particular is projective. And I want to again underline this fact, since in general this is not true. If you consider a complex torus of dimension bigger than 1, so the construction is actually the same. You consider that quotient, in this case lambda is rank to an lattice, again, which acts by translation. This is a complex manifold, but in general is not projective. To be projective, you need a polarization, an n-pole line bundle. And in this case, we call it abelian variety. Okay, so this is just to recall you how we can pass from simply in dimension 1 from a complex manifold to something which is projective and actually which has something more elliptic curve, are not only projective but also as Francesco said, they have the structure of a group and something more like the torsion point, etc. that I want to talk later, but I don't know. I hope that everything is fine, and if it is okay, I mean, you can stop me. Otherwise, I continue to talk.
Martina,
okay.
Sorry. Can you remind me what an ample line bundle is?
Okay. Yeah. I mean, just to. Okay. I don't know in this moment. Okay. If you
maybe later.
No. Yeah. I mean, okay. just to remind. I mean, just not to enter so much in details. This is the point. Okay. In this case, an ample line bundle, you can assume that. I mean, it's you have in general. You have a complex manifold. Okay, you can consider a line bundle, so something which is in the Picard group, for example. Okay, line bundle. So it is ample if there is x and n, if some of that power is very ample, which means that the map that you can construct from that line bundle, which I want to denote in this way, is not so right in this moment, but okay, this is an embedding. It's not just a formal definition, but you can assume that in this way you have this line bundle, okay? From this line bundle, you can consider the section of that line bundle, but I don't want to read, maybe it's not that line bundle that I want to consider. Maybe I want to consider some of its power, okay, just to have enough section. And if I consider that that space of the section of that power of this line bundle, and I consider, to be honest, the dual, but they are isomorphic, and the project and consider the projectivization of that vector space, I can construct this morphism. And in particular, if the line bundle L is ample, the resistance N such that this morphism is an embedding. So this guarantees the projectivity.
Okay, so if I get it correctly, you need just that one random line bundle has to be ample, not a particular one.
Yeah. I mean, there is. I mean, there exists also some a lot of theory, a lot of result about ample. What condition line bundle need to satisfy on complex torus just to be ample. Okay. So maybe then if you, I mean, it's not a random. Okay, and then.
Okay.
Yeah, I mean, it's not a random, since I take any line bundle, maybe there not exist these natural numbers such that the power is very ample. So this is the point. Okay. The fact is that I want to I can construct this morphism for sure for any line bundle that has a section. Okay. Otherwise, I go on a point. But well, I mean, let's keep that case. But I want that this morphism actually is well defined. So as not a base locus, okay? And in particular, it is an embedding. This is the point. I need a line bundle in such way that allow me to construct this morphism in such way that it is an embedding. So this is a complicated thing to say, is that the manifold is projective, since we have this embedding. Okay.
Okay. Thank you.
Yeah, I mean, it is just in this case, since I don't want to enter so much in detail about the theory of line bundle. Okay, but I mean, I think that this is one of the definition that you can find in general book of line bundle. It's not the only one, but I'm totally sure that this is one of the definition. I don't know if it's clear, or if you want, I can say something more if you prefer.
No, okay, it's fine. Thank you.
Okay, so I continue with the second part where I want to talk about morphism of elliptic curve. So as I say, I mean, as I said before, elliptic curve are also, I mean, I want to introduce this part in this way. I don't know if it is the best way, but I want to introduce in this way. An abelian group. So you can define an operation. I don't want to recall everything, but this is the operation. Which is defined by the following rule. So, okay, bad notation. So you can take the line through P and Q, and if you intersect this line with the elliptic curve, since it is defined by a cubic equation, you find 3 points, P, Q, and R. If you consider the line through R and 0, which, I mean, 0 in this case, it is the point, the infinity point. If you think about the what I told you before is the infinite point respect the Weierstrass equation. Okay. Again, if you consider the intersection, you find 3 points, and n is exactly is defined as the sum of P and Q. Okay, so you can represent in this way. This is our cubic equation, maybe. So I consider this line where here P and Q. This is R. Okay, maybe this is R. And then I consider, I don't know, I set here the 0, and then I find another intersection. Why I want to introduce this operation in this part of morphism, since, okay, the fact that elliptic curve is also a group is interesting, and one of the consequences that we can deduce, and that we deduce that elliptic curve are endowed with natural biomorphism, which are the translation, since you can define, so as consequences, as a consequence, you are natural biomorphism on E, which are the translation. So for every point P on E, you can define TP, which send each point to P plus Q, and this is a biomorphism. So actually, it's not an homomorphism, since don't preserve the structure of a group, but we are, but it is a biomorphism. And moreover, the consequences is that we have the torsion point. So we can define this subgroup of E, okay, defined as all the point of E such that P plus P m times is equal to 0. So this is a subgroup of E, actually is always finite, and M is any natural number, okay, bigger than 0. Okay, and actually an observation that I want to tell you is that if you consider M equal to 2, you are the 2 torsion point. They are really nice, since I mean, this group actually is isomorphic to this group. Okay, And you can also visualize this distortion point in general for every M, since E can be represented, as this quotient, and you can represent each point in the fundamental domain, which is this lattice. So this is a representation of my lattice. If I denote as 1 and tau, which are two complex number, but to be honest, okay, I can choose 2 random complex number as generator of my lattice. Okay, these are the vector. Okay, the 2 torsion points are exactly this one. The 0 and this one. Okay, and this group is exactly generated by this translation. And actually, since you have the translation, which are defined by the point, you have this torsion point, you can also now actually consider this group which acts on our manifold. So in particular, this hold in general, okay, for every M, but now you can take this group which act on it, and you can consider this quotient map. And why I want to focus on this quotient map, since in particular, this quotient is again an elliptic curve, and it is again an elliptic curve since you act on this manifold, on this curve by translation. They don't fix any point, and if you use the Riemann-Hurwitz formula, you deduce that the quotient is again a curve of genus 1. So it is an elliptic curve, but in particular, it is isomorphic to the same elliptic curve. Why? Since in doing this operation, you are basically rescaling your lattice. So these lattice are isometric. Okay. So this is, it's sometimes is useful to, it's also is really nice to observe this isomorphism. Okay. And so this is one of the type of morphism that we can, in particular, biomorphism that we can find naturally on our elliptic curve. But then, of course, we have other morphism that we can define, since also we can ask which are the morphism that preserve the structure of a group, and also maybe that, not necessarily from E to itself, but between different, a priori different elliptic curve. These are known as isogeny. So this is one of the type of morphism that you can find on elliptic curve. The other one are the isogeny. So an isogeny between elliptic curves. So isomorphism F from E1 to E2, such that preserve the structure of the group. So send the 0 of the group law to the 0 of the other group law. Sorry, maybe I don't say it before, but the 0 of the group law that I define above is exactly the infinite point. I denote it by 0 for that reason, okay? And here I assume that F is not constant in the definition. And basically, why isogenies are so important, since they are basically the only holomorphic map that preserve, that preserve the structure that you can find on an elliptic curve, such that preserve the structure. So you can find the translation, okay? And if you don't have the translation, the translation in particular, they are defined from E to himself, okay, to itself. But if you want to find a morphism between different elliptic curve, these are the only type of morphism that you can consider, or the constant one. And in particular, isogeny has an interesting property, since there are other definitions which are equivalent, since an isogeny is surjective always. And this follows since this image is a projective variety inside E2 but since f is not constant, it must be a curve. So this is projective here inside, and or is a point, but in this case f must be constant, or it is a curve. So it is a curve at dimension 1, and in particular E2 is irreducible, and so we deduce that f is surjective. And moreover, the kernel of f is finite, since it is the fiber over the 0 of 2, if you prefer, okay? And this is discrete, since it is a fiber, and it is closed in a compact. So it is a compact. So it's finite. This just to observe that the isogeny sometimes are defined as surjective morphism of finite kernel. And an example actually is, for example, this map. So you have, I mean, isogeny not necessarily are isomorphism, okay, since the kernel can be bigger than, I mean, it cannot be trivial. But on the other point, you have the translation, which are not isogeny, since they not preserve the group law. And just to fix an example, you can consider actually, I mean, any translation. Let us fix a translation. If you let P a point, I don't know, of order 2, if you prefer. Okay, TP is the translation. You can consider this quotient map. This map actually is an isogeny. As fine is a surjective, is a quotient map as finite kernel, so it is an isogeny. Okay, just to give you an example. But as I said before, these basically are the only the point is that I want to observe, just only to state, is that this type of maps are the only holomorphic map on elliptic curve. And why? Since I want to recall that if you define a map, I mean, this is the point, isogeny, basically, maybe are the only holomorphic map on elliptic curve. Since if you have a map between elliptic curves, let's denote this elliptic curve in this way, where these are rank to lattice. Okay, we have that universal covering, this universal covering, and so F, since the universal covering is unique, leads to a map from C to C. So universal covering is unique, and we obtain a lift of F, and this lift is a an holomorphic map, and in particular satisfy this condition. So holomorphic map between elliptic curve basically are this type, and these are linear map. One can prove that they are linear map. Okay, so what you get is that if you consider an holomorphic map such that also preserve the structure of the group law, you get a bijection with any complex number such that satisfy this condition. Since for every complex number, you can define this map where phi alpha is defined in this way. And this set are exactly the isogenies. Okay, they are the morphism of elliptic curve that preserve the structure of a group. So these and these exactly describe all this type of maps. Of holomorphic map. So this is why when one talks about isogeny, the other point that I want also to underline, that I assume that they are not constant. Otherwise, if you assume that, if I don't assume that condition, the other maps that I can find on elliptic curve that preserve also the group law are exactly the constant one. Okay, which is the map 0. So, but you can, is the trivial one, but you can skip that that case. And I don't know if I was a little bit confused, but I don't know if it's clear, if you have any question, but this just to say that we have different type of morphism. So just to summarize, on elliptic curve, you have the translation, which are only biolomorphism. Otherwise, you have the isogeny, which are of this type. And of course, isogeny can also be specialized in this case. I mean, basically, isogeny define the homomorphism between elliptic curves and they are exactly if you consider E1 equal to isomorphic to E2, you get the endomorphism ring. So again, this is the endomorphism, which is a special case of isogenies. And just to recall that, an interesting thing is that this ring is isomorphic to the ring of the integer in general, if you don't assume that elliptic curve a complex multiplication. But I just don't want to enter so much in details about morphism of elliptic curve. So that's all. Just to say that there is this bijection. This is the main point of the second part. It's clear. I just wanted to say something about the last part about Jacobian, just really quickly, since I don't know how much time we have. But if there are no questions.
I just wanted to make just a short remark about the fact that the same proof that Martina used for the groups of 2 torsion points, you can obviously use it also for n torsion points for every order n. And in fact, all these phenomena that occur in the complex case are in some sense the base in order to recover similar results whenever you change the base fields, including these facts about torsion points. When you will work with elliptic curves over other fields, you will obtain that torsion points will satisfy a very similar behavior even on different fields.
Thanks for the remark. So I continue with last part about the Jacobian of a curve. So to be honest, this can be this element, this mathematical object can be introduced for every curve, and this I don't know, I want to introduce it in general, and then I want to specialize since it has a geometrical interpretation for every curves. And in particular, when you specialize this Jacobian for elliptic curve, we can say we are able to say something more, and with something which is really interesting. So if you let us see a curve of genus G, okay, you can define this group, which is the set of the group of divisor. Basically, divisor is a formal sum of point of our curve times a certain number, and P is any integer number, but it's just a formal sum. And this is the group of divisor. Inside this group, you can find the principal divisor, which are divisor defined by meromorphic function. These are called principal divisor. Okay. Also, I have to recall that there exists this map. You can define the degree of a divisor. So we have this map from this group to Z, which send any divisor to this one. And if you consider F a meromorphic function, then one can prove, you can assume as a factor that the degree of the divisor associated to F is exactly equal to 0. I don't know if it is clear what are these type of divisor, but if you consider meromorphic function is something that you can write a meromorphic function as a rational function. And so, for example, just to, I don't know if for everyone is clear. So the divisor is exactly the 0 of the function minus the pose. And here you can get that here we get the 0, here we get the pose. Okay. And basically, if you get the degree of that part is equal to the degree of the pole. This is the idea. The 0, these are the poles. And so why I say these things? Since in particular, you can also define another subgroup inside the group of divisor, which are the degree 0 divisor. Inside that group, you can find the principal divisor. These are subgroup, okay, not just inclusion, okay? And so one of the questions is to ask, what are the degree 0 divisor which not arise from principal divisor? So what is this group? This is the question to introduce the Jacobian, since the answer is that this group is exactly the Jacobian as a group. Now I introduce what is the Jacobian, but the answer to give you what is the, to be honest, it is a manifold, a Jacobian, which as a group parameterize this type of group, and it holds for every course. Okay, so this is the question to introduce that that object. Now, how we can define how it's defined the Jacobian of a curve. So you have a curve C. You can consider this space of holomorphic one form. You can consider the homological group, which is the fundamental group. Okay, so it has 2G generator. Okay, and for every loop in well, okay, if you prefer here in this homological group, you can define this map, which send each one holomorphic one form to this integral. And so, to be honest, you define this map alpha from H1 to the dual of this space, which send each loop here. Okay, and so if you consider the image of this map, it is a lattice that actually acts on that space, which is isomorphic to CZ. So the G the power G. So this is a lattice which acts here. So we define. The Jacobian is defined exactly in that way of G of genus G is this quotient. which is a complex torus of dimension G. And what I want to tell you is that this is a manifold. It is also a group. I mean, the fact that it is a group, it's also in higher dimension. And as a group, it is actually isomorphic to that group. I don't want to prove, since I'm not able to prove the Abel theorem, but the point is that how we can construct that map. Abel and Jacobi construct this map. So if you fix a point P0 on the curve C, you can define the map mu from C to the Jacobian, which send each point to this integral, where omega 1 and omega g are a basis of the space of holomorphic one form, which has dimension G, exactly the genus of the curve, okay? And in particular, this map, okay, one can prove that it is holomorphic. Of course, it depends on the point P, if P0, but if we change that P, the different, I mean, the image different from strong translation for something which belongs here. And moreover, that map can be extended here on the divisor of the degree 0 divisor in that way. So it is an extension. And now we finish. Since here sent to, okay. Since now Abel proved that this map is surjective. This is known as an inversion problem of Abel, if I remember well. Okay, and moreover, the kernel of that map are exactly the principal divisor. So if you remember, I defined that group X0 as this quotient. And by the first theorem of isomorphism, we get this isomorphism as group. Okay, you have this is a morphism of is an homomorphism. Okay. So for every curve, you can define this complex torus of dimension G, which as group parameterize all the degree 0 divisor, which are not principal. And moreover, if you specialize the case of genus 1 curve, we can say something more, since it holds the following lemma, just only to state that every elliptic curve, so here I denote C by he, is isomorphic to this group as group. I don't want to prove, but just to give you an idea how we can define this isomorphism in that way. We have to send each point to a degree 0 divisor in particular. So how we can do this, we can construct this homomorphism. We have a special point on each elliptic curve, since an elliptic curve is the neutral element. So we can send each point P to P minus 0, which is a degree 0 divisor, and then you can prove that actually it is an homomorphism and bijective. So it is an isomorphism of group. And so what you get for elliptic curve is not just that the Jacobian described this group, but actually it is isomorphic to the same curves. The fact is that you have that diagram E to the Jacobian, which is the map mu. Here we have this isomorphism. here we have this isomorphism. The point is that since in this case, the Jacobian is a complex torus of dimension 1, since the genus is 1, mu actually is an isogeny, since it is a morphism which is not trivial between elliptic curve. So it is surjective and finite kernel. And the kernel is trivial since these are isomorphism. So we get that E is isomorphic for sure as group, but moreover, since we know that mu is holomorphic, they are dualomorphic, so as manifold. So the point is that mu is holomorphic. This proves that mu is bijective, since we have these two isomorphism. And this proves that in this particular case, for elliptic curves, we have this isomorphism as manifold, so as curve is a biolomorphism. And this is what I want to say about the Jacobian. I think I don't know if you have I have some question, but otherwise I think it's a good moment to stop.
So is there any question or comment?
Well, I have one maybe. So you mentioned before that of course elliptic curves are groups, right? But I assume they are Lie groups in some sense, of course, because of the definition of the translations, right?
I think yes, but you have to, yeah, Lie groups are manifold, which are also group. I don't remember the definition.
They are
sorry.
complex. Well, they are complex manifolds, so I assume they are complex Lie groups.
Yeah, they are complex Lie groups.
Yeah.
Okay.
Yeah.
So my question is, I don't know if you can tell me something about maybe the Lie algebra of these elliptic curves. Is there any?
No, I don't know. I don't know if someone know the answer, but
I would say I'm not well informed about that, but there are surely results about that. It's just that I never got interested in that, but there are surely results about this kind of things.
Okay, no worries.
Yeah, I mean, no.
Is there any other comment or remark?
I just wanted to make a couple of remarks about the Jacobian, just also to, in some sense, justify why it is important for elliptic curves, not only because of this isomorphism that Martina explained to us, but I would say also for two additional reasons. The first one is that starting from this isomorphism, in fact, you can construct what is called the dual of an isogeny. You start with an isogeny between elliptic curves. Then
yeah, if you want, I write when you speak.
Okay, as you wish. Exactly, you start from an isogeny, and this induces, in fact, a morphism between the Jacobians of your two elliptic curves. And since you have the isomorphism, if you use these induced maps on the Jacobians and the isomorphism between elliptic curves and Jacobians, you can in fact define an isogeny between E2 and E1, which is called the dual isogeny, which has some important properties, is well linked with your starting isogeny. And the fact that these dual isogenies exist is something that is really used also in computational applications, because a lot of elliptic curve cryptography also uses isogenies between elliptic curves. And yes, this was just the first remark. The second one was simply that, as Martina said before, you can define the Jacobian for every curve. And this is very useful because the idea is that if you want to study some problem, for example, some arithmetic problem on curves which are not elliptic curves, you can use the Jacobian and try to shift your original problem onto a problem of elliptic curves. And then you can hope to recover some information for your original curve by studying the Jacobian of the curves. And this is usually easier because the Jacobian, since it is an elliptic curve, you obtain has a lot of properties that your original curves does not have. Okay, these were just my 2 remarks about the Jacobian.
Okay, is there any question, any other question or comments? If not, let's thank our speaker again.
Thank you very much, Martina, for the talk.
And we resume next week. Thank you.